Hello, everyone. Good afternoon, good evening, welcome. This set exam, as some of you recognized, this one is from USNCO 2026 National Exam. Right. You compare the solution, and if you really wanted to make it to the high honor, you should target 50 and above. Then you will make a high honor. So unlike the local exam decode, this time I want to slow down a little bit. So not only discuss this question, I'm going to expand a little bit so that I'm going to divide this set exam to 2 times. Today, I'm going to cover 5 topics, 30 questions. Next time, I'm going to cover another 30 questions. So I'm going to divide. Got it? Okay. Now let's do that. Let's do one by one. Let's do by one. Okay, for the first question, I think it is the easy one, right? You look at this is the very simple question. So basically, it is very basic of stoichiometry. However, I do want to expand this question, okay? Now, let's finish this one first. What do we have? Right. Copper sulfate, pentahydride, when we heat it, it's the first step, of course, will remove all the water, okay? The water of hydration, right? So you got now the question said, how much colorless anhydride, copper sulfate, with beginning 10 grams of blue copper sulfate, pentahydride. So if I set X, since here we use mass in the same column, we use the same unit, which the molar mass 249.7 grams. Reaction coefficient is 1. It's 1 mole. So basically it's 249.7 grams from what? And 159.6 grams. You solve this question. So you should get 6.391 grams. Since here it is a 4 significant figure, so I want you to keep 4 significant figure. If your answer get this one, give yourself +1. Give yourself +1, okay? Now, as you know that copper, especially copper sulfate, copper nitrate, copper chloride, has been used in the USNCO and IHL Olympiad all the time. Copper sulfate, copper 2 nitrate, copper 2 chloride. Very common one used in the exam, okay? Now, here I wanted to discuss in terms of Olympiad learning from this question, what we can learn. You remember copper, argon, copper is a 29, right? You have a 4s2, 3d10. Did you remember last Wednesday we did? Why is it 10? So we discussed exchange energy. Did you remember? Now, when we lose electrons, we can lose 1 electron. we can lose 2 electrons. So when lose 1 electron, which means most of the time it is a solid state. Solid state is a stable. In the aqueous solution, it's not that stable. Now, lose 2 electrons, we got argon 3D9. Remember, 3D9, D9, D4, you need to pay great attention, right? Carbon 2 is a D9. D9, anyone can tell me something? That one will have a stronger, very stronger, called Taylor distortion. Right? Very strong distortion. And every time when you see copper, very likely question were related D9 stronger John Taylor distortion. So in this case, always it's 1 unpaired electron. So when you have this distortion, stronger distortion, what will happen? And in this case, will affect geometry. Right? And look at D10, couple 1. What's the shape? Normal. What's the shape will be? Anyone know? And that shape could be linear, could be tetrahedral. How about the D9? And that one could be square planar. And or you change the d orbital, right? Or octahedral. Octahedral. Okay. Why? Because John Taylor distortion. And it has been in the exam all the time, not only this country, around the world. To summary, always make spectroscopic connection. When you see carbon 2, always make spectroscopic connection. So which means the disturbed crystal field exchange, you change the energy of the d orbital. To change the energy of the d orbitals, leading to characteristics changes in electronic observation spectrum. So that's why carbon 2 complex often shall have a broad, asymmetric, visible absorbing bands, not a sharp band. Not a sharp band. So many transition metal ions, and that band is very sharp. Sharp bands. But for the copper, it is broad, asymmetric, visible absorbing bands. Remember, come from here, come from this one, come from this one. Okay, so that's the one. Very nice question, and I'm very positive. Sooner or later, we'll have a question related to this one. Make a connection with spectroscopic connection. So that's I said Olympiad learning. In the future, I will add this topic. So when we then do this question, you can change. You get thousands, hundreds of questions. There's no way you can finish all the questions. But when we do question, I want the class reflect, do some reflection, understand what's mean. As you see this one, see what's this? This is bluish. This is colorless. That's colorless. Okay. Related to spectroscopy. You understand this background, you will make everything is so easy. Or another thing we can say, couple two, high spin or low spin. Right. Couple two, tell me high spin or low spin. Couple two. High or low? High spin or low spin? Right. To answer this question, you look at, so that question probably related to what? Related to D4 to D7. D4, D7 will have a high or low. However, couple two, there is only one unpaired electron. See, only one unpaired electron. Right? Only one in octahedron field, regardless of ligand strength. There's only one unpaired electron. Larry? Right? Regardless, it's a ligand strength. Very nice question. Now, let's go to next one. So that's why today I want to do this way. Now, slow down a little bit. Not like last time, rush. Go to next one. This question is about stoichiometry. And the first step, when you do this question, when you see it cannot be determined from the information given, I will be very careful. Anytime when you see this choice, make a question a little bit of challenge, okay? So let's look at it. The question is very simple. It is a combustion reaction. So I'm right here. Right? It is combustion reaction. Now listen, when anytime related to stoichiometry or give you the chemical reactions, you have to check the balanced chemical equation. Although it seems balanced, you have to check. Never assume that reaction is balanced. That I will say, okay, the second one, in this one, you pay attention states. See, here is a gas, here is a gas, here is a gas, here is a liquid. So liquid, which means we can assume not occupy the space. That's the first thing I wanted to say. The second one, when you see what? When you see STP, and I will suggest you treat it as a constant. Why? Under the STP, any gas, any one more gas, occupy 22.4 liter. With Na molecules. So treat this one as a constant. Now, in this case, initial, you get initial is a 22.4 liter. Now, you are going to have a reaction. After the reaction, you return the condition. So T equal T after the reaction. You get what? You get a 11.2 liter. So what's the information we have? As we know that STP, any one more gas occupy 22.4 liters. So that I can say here it's one more. I can put 3 sigma in the figure, okay? 3 sigma figure, I put, now here it is what? Here it is a 0.50 mole. 2 second equals 3. Should I put a 0? 1 more 0. 1 more 0. Okay. Right. Now the question said, how many this one initial original present? And its answer should be this. Why? So when, in this case, basically question related to what? Related to stoichiometry and the limiting agent. Limiting agent, okay? Right? So yes, look at the change from initial to the end. And then you can see the amount of a substance reduced to 0.500 mole. So if we put a minus, right? If I said initial, this one, ethane, X. Now oxygen should be 1 minus X mole. If I said oxygen excess, so that this one is a limiting agent. Limiting agent, see, look at. So you left over is a 0.500 mole equal what? Equal carbon dioxide and oxygen left. Very simple, right? Those are questions we are going to practice a lot during the course of the class, okay? We are going to do a lot. Now, in this case, the relationship 2 to 4, so that one, you get X, that should be 2X. Right? 9 plus is what? It is 1 minus X. Now you minus what? You consume 1 to 7, so that it's a 0.5X. In this equation, there is only one unknown, so which is X, 0.200 mole, C2H6. Right? Now, next one is the same way. Can I say C2F6 excess? Now, in this case, the limiting agent now is this one. It's this one. That's the limiting agent, okay? So the relationship here is a 7 to 4. So that 0.55 equal what? Equal carbon dioxide and C2H6 left. Do the math. That should be 471 minus X. I like to do the math. When I was in the high school, I really enjoyed doing this math. Asian country do this question all the time. This type of question, okay? Now you get what? X plus, minus, not the plus. Should it be minus, right? You minus 071 minus X. Now you solve this equation. There's only one no. You do not use X. Do not have use X. You can use Y. Then you get X. It is a 0.300 mole. C2H6. Now, and this question, based on the information we have, we cannot determine. We cannot determine. Class, I want you to know, we are going to do a lot of these types of questions. You basically, based on stoichiometry calculation, you will get unknown. You get X, Y. Then you are going to do, if X equal 1, Y equal sum. If X equal 2, you are going to do that. You get the final results. And that's the trend. I promise you. That's the trend, okay? So what do we learn here? See, I try to in the class or the question solving, I try to use some Olympiad learning. In this case, since the problem give us initial mole, the final mole, and the balance equation. So we need to choose what? The key point is that we normally determine extent of the reaction. So in this regard, we will discuss more when we discuss chemical equilibrium. Chemical equilibrium, okay? Right? So this question, it is classical the Olympiad exam. Reaction extent not equal initial amount. And we needed to determine which one is limiting. Example 2. Now, your choice should be D. Give yourself one more plus. Okay, one more plus if you get it right. Okay, go to next one. Any learning? Oh, here is the learning. Okay. Use equivalent mass, not just the molar mass, because the acid you can donate one more proton. That's a good one. That's a good one. This is a very good one. I believe we did, maybe not the last year, 1 year. It's a very nice question. You have to times how many proton? Yeah, we will try that question. Okay, during the exam. Let's look at. Let's look at. So what's this? So we have white solid. Remember, it is a white solid. Why this is important? Sometimes you can ignore. Sometimes it's lots of information, which means you have a stronger intermolecular force. It is a solid. And that one, it is organic solvent, organic acid. Did you remember? We in the lab training, we discussed benzonic acid, oxalatic acid. That's a common acid when you do the lab. We're not HCl. We're not sulfonic acid, phosphoric acid. It's not. Here it's white solid. That tell you it is organic acid. See, indeed. Indeed. And if you want me to choose, I will choose this one. To be honest, then we can do. What's this? This one is this one. See? Oxalatic acid, as you know, oxalatic acid, it is very common acid during the exam. Why? We can do acid-base titration. Primary standard. We can do redox titration, primary standard. When we do the titration, because Ka1 divided Ka2, and we're less than 10⁵ power, so that you will not see two equivalent points. We're not. You got it? So this is a very common one. Not only common, this one, what? If you got how are we going to calculate the pH? That is very unique way to calculate pH is that 1/2 pKa1 and pKa2. Why? Because this is amphoteric. Just like amino acid. You got it? Yeah. So that's why, class, I really want when you do something, you slow down a little bit, think about, okay, oxalatic acid. Now let's do that. If I were to, what's the choice? What's the choice? Right? So what do you have? You have a mass. You titrate with a base, stronger base. So the equivalent point probably will be, not the probably, will be equivalent, the pH at the equivalent point will greater 7. Will greater 7. Now use what? Use phenolphthalein, and that should be 8 to 9. 8 to 9. Right? So tell us this one, it is a weak acid. It is organic weak acid. So in order to do that, we need to find the molar mass. Right? Molar mass equal what? equal mass more. How did you get more? So here it's 1. So that was assume it's 1:1 ratio. Then you do that. You do that. Okay, it's a 0.2700. Why is this one? Titration. It's not a 0.27. It's not a 0.3. It's a 0.2700. Why? That's a titration. You weigh the mass. You got it. Each question. I like this set of question. When we finish this part, you go back to reflect. You said, I should get at least 58. I should get perfect. But why we cannot get it? Then we are going to reflect for the next year, following years. That's what I wanted to say. Okay, now let's do that. Let's do that. So here is what? Here it is 3270 times 0.1834. Look at the data process. Then you times minus 30. Why? More. You get more, right? So you get what? You get 45.0 more. Now here it's not more. It's not more. Why? Because the acid could have 1 proton, 2 proton. Back to China, what do we do? We never use more. We use normality. Normality. Asian country use normality. Normality. It's use N. Why is it important? Very important. Very convenient. US do not use it. Such as we do redox titration. How can you calculate? How many electron gets? You ask the base titration. So such as if HCl is 1.00 N, also equal what? 1.00 M. However, for this one, it's 1.00 M. It should be 2.00 N. In this case, you consider proton. How many protons? Yeah. But we do not have use that one. You need to pay attention. So it's not, the molar mass is not just 45. It's just not 45, okay? Right? It's not just 45. Now let's go back. So you find this one. Now, look at the A. This one, yes, it is a 45. It's right. It is a 45 gram per mole. That exactly is a mole. You have only 1 proton. Only 1 proton. However, do you think that one is a solid? No, it's not a solid, okay? It's not a solid. Now, the second one is a 46 mole. You have 1 proton. So you have 1 proton, 1 acidic proton. Now look at this one. That one is a 45. That's a 45. Now, its molar mass is what? It is a 90. It's a 90. Here it's a 45. Molar mass is 90. Basically, it's what? You have 2 acidic proton. 2 acidic proton. Okay. Now, next one, that is a 92 more. You have a 2 acidic proton. If you get what? You get a 46. Right. So in this case, when we look at this one, now, it should be A and C that fit. However, this one, of course, is not stable too. This one is not stable. And also, I don't think that one will be solid. You look at it, will be not solid. Okay, should it be liquid? It's not a stable liquid. Now, that's the way approach. So it's what? It's oxalatic acid. Remember, oxalatic acid, people love it. Love in the exam. Yeah, believe me, you look at next year and following year, look at it, you see it all the time, right? Primary standard, primary reference for acid-base titration, redox titration, and with the titration, it's normal, regular, the curve, you will not see the first equivalent point, you will not. Why? Because Ka1 divided Ka2 is less than 10 to the fifth power. And they said I get very confused. That's okay. We are going to do that. We just get started. And also, if such as a sodium hydrogen oxidate, that's the way calculated pH. That's the way calculated pH. Okay, very good. We'll finish this one. Okay, go to next one. Go to next one. Okay. This is a very good one too. This is a very good one too. So what's this? So what are we going to calculate? Let me look at it. So how are we going to calculate? Aqueous, this one, absorbing this one, this one, this one. Okay. Okay. Okay, got it. Read it one more time. Okay, read it one more time. This is a very nice one. So related lab. Aqueous sodium sodium hydroxide absorbing carbon dioxide, all course. Right. In the class, in this level, I really want everyone always use net ionic equation. Well, from hydrogen carbonate, of course, that's 1-to-1 ratio. Could it be 1-to-2 ratio from carbonate? Always use net ionic equation, right? And also remember, that's the reaction. Also, carbon dioxide can dissolve to the water. And of course, partial of dissolved carbon dioxide will form carbonic acid, but that process is very little. Anyone remember we discussed? So most carbon dioxide dissolved to the water, very few percentage form carbonic acid. That's why when we look at the Ka1, it's very small compared to common diprotic acid. This one is very small. The small is what? We assume all dissolved carbon dioxide form carbonic acid. Actually, it's not. It's not. Again, we will discuss this part. Was in the exam many times. Okay, so the two processes in here. So one process, the first experiment is just the pure dissolved. The second one, you have a reaction. You have a reaction, right? So what do you want to find? You wanted to find the concentration of sodium hydroxide. Now, let me give you the answer. Okay, you get your point. You should get 0.169 molality. That's your answer. How do you get this one? How do you get this one? And the way to calculate molality is M, you get mole. U times the volume, liter. And that's the way to do that. Mole times, now, so we need to find the mole. Through what? Through this reaction. Now let's do it one by one. Very cool question. Very cool question. So again, this question reminded me, as I said, this year have a major shift. Not from A directly go to B. We are going to hunting X on the moon, not on the Earth. But what is X? What is X? Okay. So you have two experiments. The first one, and it's what? Basically, you look at the pressure drop. See? You look at the temperature is the same. The pressure, see? Carbon dioxide introduced in the head space at the pressure 1.33, just a Coca-Cola. You see, look at the can. So sometimes you cannot see it, right? And now the decrease to 1.00 atm. See, then I tell you, absorb into this one. Even before has it, right? So in this case, the pressure drop. It's what? It's 1.33 atm. You minus 1.00 atm. You get what? You get 0.33 atm. Now, we do not have to, right? Now it's what? So basically what? Remove N carbon dioxide, removed from gas. And PVRT, if we give you this equation, everyone can understand, okay? So we have a P, we have a V, you have a constant, so you get what? You get a 0.1348 mole. Now here I introduce actual significant figure. I introduce actual significant figure. Why? Just, later on. See, here it's not a multiple choice, my friend. Not a multiple choice, okay? Right? So now, look at it. In the solution, how many mole? Sodium hydroxide, and that one, can I say it's 1.00 liter times 0.100, right? So this is a 0.100 mole. Although you remove this many more, but react with the base, you consume this one. Now you get what? So we can calculate the dissolved. That's the soft, not the soft, dissolved. Dissolve the carbon dioxide. Do you think it is 0.0348 mole? But remember, that's the 1 atm. So that's the first experiment. We know that. Now look at the second experiment. The second experiment is the drop, pressure drop. It's what? It's 1.50 minus 1. You get a 0.5 atm. Right? Now we can simply use the same way, calculate how many mole should equal 0.44 mole. How can you do that? N equal PVRT. Again, in this case, how many physical dissolve? Physical dissolve is this one. Physically dissolve, right? So now that's dropped. You physically dissolve this one. Now the react with we can calculate, right? Which is a 0.2044 minus 0.348. You get a 0.169 more. Here it's a reaction. Where is my reaction here? See, it's a 1-to-1 reaction. So that we can calculate or OH minus equal 0.1696 mole. You divide 1.0 liter. So you get a 0.1696. If I keep 4, it's this one. If I keep 3, should it be 1.170? Okay, that's the way to do that. It's really cool. And if this question said, I ask you to calculate the molality of sodium hydroxide, it's so easy. However, through 2 experiments, logical, critical thinking, not only that, but also is what? Use this principle. Use this principle, okay? Sodium carbon dioxide is very unique. Very unique. The solubility pretty high, pretty soluble. However, the way from the carbonic acid, it's very little. That's why you make a Ka1. It's very little, okay? Very nice question. Very nice question, okay? Now here, when I do this question, in my mind is what? So it's a very good Olympiad question. Involve what? Ideal gas law, gas solubility, stoichiometry, calibration experiment. The trick for this one, for first experiment, you need to find physical, not a chemical change, physical change, how much dissolves in the water. Yeah. Then use a second experiment to calculate how much sodium hydroxide used, reacted. You know, we know the volume, you know the molality. Very nice, very nice, very nice, okay? Yeah, I'll go to next one. This is the easy one, okay? This is the easy one, right? That's the easy one. So the quick do that is what? See, you need to find the molar concentration, basically it's molality, okay? And that should be equal 0.600 m. And I use what? So here, what I learned from here, this is a classical count of ions. You divide the total volume. For mixture of stronger electrolyte, you calculate the mole. Then you add the mole, you divide the total volume. That's the way. However, there's one simple way to do that. One simple way, which is, I said weighted. Basically like what we calculate. Now, do you know how to calculate the atomic mass of element, like hydrogen? We use weighted average, right? It's weighted average of all isotopes of that element, such as Cl17. You have what? You have the mass (35%). You plus the mass. Cl, not 35, not here. 35 and 37. That's the way you calculate this one, 17. And here we can use the same one. That's not only this one. Did you remember we can calculate the gas too? You have a different container connected together, different volume, different pressure. Then we open all. Then what's the final one? Did you remember? And that P, the final pressure, should be P1 V1, P2 V2, P3 V3, and it's V1, V2, V3. That's 2 examples. Now here's the same. The quick to do that is what? Molarity, volume, N. Let's do 1, 1, 1, 2, and 2. Then you get what? V1, V2, V3, VI. Right, that's the way to do that. Weighted. Okay, what's the mean N? Oh, let me slow down a little bit, okay? The N, which means in this case, see, that's the 1, N equal 1. In this one, N equal 2. In this one, N equal 3. So in this one, you do that. Now let's do that. So you get a 0.100 times 0.100 times 1, 2 times 2, 3. Now you get what? You get 0.600. Here it's a liter. And in the top, it's a mole of ion. So you get what? You get 0.600. That's the way. Okay. Now let's move on. Plus, I will suggest it one more time. Every time when you do the one question, if you can do some summary, that's will be great. Now, if we do this one, next time we have a similar question, do you think it takes only 20 seconds? So it's no time to think. USNCO Olympiad exam is a race, not an exam. Okay, go to this one. This is the easy one. This is the easy one, right? So you look at this one, when you see that, that one is related selective property of osmotic pressure. Osmotic pressure, okay. Right. And the key point is what? Osmotic pressure use pi. It's IMRT. Remember, M is molarity, okay? Molarity. Should there be more per liter, okay? For the freezing point depression, boiling point elevation is the smaller m. That's called molarity. This is molarity, right? So basically, it's what you look at this two. You look at these two. Now, if I equal 1, which means non-electrolyte, I equal 1. So in this case, do we have it? Let's look at it. Oh, here. Sugar is a non-electrolyte. Now, for next one where we see here, and that is a sodium chloride. For the sodium chloride, and the N, I should be closer to the 2. Closer to the 2, not the 2, less 2. And that one should be less 2. Why? Ion pair effect. Ion pair effect in the exam all the time, especially in USNCO ion pair. That should be less. No, I'm not going to write it this way. That should be less 2. Not very much. Now you can look at, based here, what we can do. IM for the sugar, 100% is 0.2. 0.2, okay. Now for sodium chloride, and that one IM should be close to the 0.3. Now you know that, right? You know that. You know that you get based on chemical potential, basic chemical potential, because this one in the left side, in the right side is a sodium, and this one it is a sugar. That is a sugar. The water will go to from left to the right until the chemical potential reach the equilibrium. So the choice, you choose A, you get another point. You get another point, okay? Remember. So we will discuss in the thermodynamics. This year, we will introduce chemical potential. How we are going to calculate chemical potential. Chemical potential not only depends on the P, but also depends on the N or molar fraction. We're going to do that, okay? We're going to do that. In this case, of course, related this one, because the temperature and the pressure is the same, right? So those are questions. Okay, go next one. Now here, see, what's my takeaway? What's learning point? Oh, also particle pressure. Membranes only allow the water to pass through, water to the side with larger concentration dissolved particle. I use a particle. Why? That particle could be molecules. That particle could be ions. Use a particle. Okay. What do we can learn? So we compare total number of particles. Not molarity is this one. Use this one. Okay. You got it? Yeah, that's the way. Okay, go to the next one. What do you think? Do you think this is help? Yes? Okay. No response. That's fine. Look at this relation. That is just common sense. Just common sense. They said gas mixture distinguished fire, but does not make the lemon water to cloud. What's this mean? Which means that reaction is this one. See, it's lemon water. That's a lemon water. Solubility not great. When you bubble carbon dioxide, so we get like milk, okay? Now get water. You know this reaction how important, right? And that reaction have two purposes. The purpose number one, you can test carbon dioxide, or you can test lemon water, both. So if you have carbon dioxide, you bubble to the solution, you get cloud mucilage. That's very likely is the calcium hydroxide. Or if you know the calcium hydroxide, just like here, you bubble gas, you get a mucilage, that's a carbon dioxide. Okay, so you know this one. And you should know the very basic physical property of chemical property of the common gas, okay? Right? So they said, not where this one, that sentence tells us no, this one. Now, when there is no, this one will make this one, distinguish this one, will distinguish, which means there is no oxygen. The choice, you should choose this one. No carbon dioxide, no oxygen. And very likely is what? Very likely will have a nitrogen. That's a common one. Or maybe if very rich, you can use argon or inert gases based on the property here. Right? So that's the one, not the hard one. This is the easy one. Now it's here. What do we learn? That one test is not a definite test for complete or opposite this one. However, in all the choice, all is a positive, and this one is negative. So that, yeah, that's the one. I will choose. This question is very odd. This question is very odd. I do not know how to get this question. Let me tell you the truth. But easy to understand. Very easy to get right. Do you know why? What's this? That is what condensation, right? That is a condenser. This one is a condenser for the chemical reaction. Refraction, right? Refraction. Or distillation, we are going to use it. What's this? That one is a graduated cylinder, measuring. What's this? And that one is a burette, titration, measuring. What's this? That's called a test tube. It's just a name. Tell you the truth. No one uses this one. No one uses it. 50 years ago, not 50 ago, when I was in the college, it's 1979 to 1983. We never used it, even going to China. I do not know where to get this question, but I will tell you what's the purpose of this one. That called this is a tube called to measure the melting point. To measure melting point, what they did, they put the oil. They put the oil. That's the first step. They put the heating oil in here. Now the second step, they put the thermometer. The third step, put capillary tube. Then you heat it here. And the design for this tube is what? So you heat it here, and the oil, I'm not Joe well. See, all the way go to here. And you heat it, and it's a heated oil where what? Where secret. You keep the temperature. So keep the same temperature. That's the shape. See, you heat it here, you heat it, the hot water go to this way, or you go to this way. You keep the temperature evenly. That's the one. So what's this one? You measure the organic. You choose this one. Choose this one. See, and that is operate. Right now, what? Number one, used to be any new compounds, you make it. Right? You make it. You are going to publish the paper in JOC, Journal of Organic Chemistry, or JACS. That's probably the best journals in the world. You have to include the melting point. You have to include, you need to measure the melting point. Now, in the last 30 years, no, you do not have to. Such as when I filed the patent, used to be you have to include the melting point, the physical property. Right now, use what? We use mass spectra. We use NMR. So you only need to include this one. So no one uses it. In my life, I never saw this one. Even when we measure the melting point, it's much better than this one. Okay, but that's the way. So which also tell us that the common, even old glassware, what's the function? You do not need to memorize, but you should, at least you should know that. That's why I'm going to dig out, find old experimental menu and make a copy, send it to you. So you just look at it, take 5 minutes, now you got it. If you see this one, you do not need to think about, but you should get it right. That's the only choice. So look at it here. Right now, we barely measure the melting point for sure, But if you wanted to measure it, all is digital. Right? The setup, you have this, heating oil, okay? Now you put a thermometer, you put capillary tube, you have a sample. How are you going to put the sample to the capillary tube? That's another technique. We are not going to go this way, okay? Now, if you ready go to camp, go to the IHL, I will show you how to do that. So it's a way to do that. Okay, so it's a way. Right. Now, next one, you heat in this side so that, see, the special shape, this one make a sure circulation so that the temperature in the oil all is evenly. You will get good measurement. That's the one. Yeah, that's cool. This question is interesting. When I see it, why my God, a question like this, now go to next one. Again, physical is a descriptive chemistry. Descriptive chemistry. Lesson class. Do you think we need to spend more time working in this part? Physically, chemically, the unique physical property, the unique chemical property, the unique application, the unique approach to make it. That's called the descriptive chemistry. Indeed, some you need to remember. We are going to spend more time. Let's look at here. So, which gas can be condensed to the blue liquid? Of course, there's no way. That's the only choice. That's the only choice. Right? This one, carbon dioxide, it is a colorless liquid, colorless solid. However, carbon dioxide solid, the direct go to what? To go to sublimation. Why? You look at, so everyone need to pay attention, phase diagram. Carbon dioxide phase diagram, you need to know 100%. That's the one. The second one, S8. You have to know that. The third one, bromine. This is three common one. The phase diagram, you should know that. You should know very well, okay? Has been used all the time. This one multiple times. This one were not many times in this country. I think this year before the exam, we did a question like this. Okay, let's go ahead. So hydrogen, we know that. Hydrogen is a colorless liquid. This one says color. And the red color should from yellowish to brown. And everyone should know this one. Could it be right? So what's this? Here, this one is colorless. This one is brown, and used in the chemical equilibrium all the time. Now, and what's this? That is a brown. Of course, can there's a reddish, brownish. That one is a blue. Even gas, just some color, it's a light blue. Light blue. See, this one is a light blue. It's a light blue. Now become liquid. That's a deep blue. That makes sense, concentration, right? And you know ozone, right? You know ozone. What's the application ozone common one? Anyone remember? Oxygen, you bubble to the high voltage, right? Your high voltage, you get what? Now, in the minus 78 degree, which how can you make it? The way to make it is that use acetone dry ice. You add acetone. You will get a -78. Very easy to make it. Now you react with what? You react with double bond. Right? Now, depends the condition class. If under reduced environment, such as right, you get what? You basically get aldehyde. You basically get aldehyde. Okay. Right. If no reduced environment, you get what? You get all the way go to the acid. What's significant? Before you have a spectroscopy, this reaction to determine how many double bond or triple bond, where is the double bond and the triple bond, and play significant role to determine the structure of organic compound. So ozone, yeah, that's the reason they choose ozone. Okay, it's very one. Now in this case, I give you some help. Okay, right. So this one is a colorless gas, but liquid, lightly blue. This one is a blue, deep blue. This one brownish, yellow brown. This one greenish, yellow. This one is red brown and red brown. So those you need to remember, class. So you need to words remember. Okay. Yeah. It's not fun. I'm not the person to memorize the to remember like this, but actually sometimes you have to. Okay, now go to next one. What's the learning point? Both liquid oxygen, liquid ozone is blue. However, liquid ozone is much darker, deep blue. Okay, remember different. Now go to next one. This is the easy one. This is the easy one. Now the choice 9 is a D. Give yourself +1. 10. The 10 is B, the choice. Give yourself +1. This is the easy one. This is a question about what? And we know that solubility, right? Solubility law. Okay, we know that. 2 liquid soluble or in all proportion. The basic what? And like dissolve to like. Like dissolve to like. So polarity, why? Because the solubility from structure point, it's related to polarity. Polar solute, polar solvent will make a solution. Ionic compound will dissolve polar solvent. Non-polar solute, non-polar solvent will make a solution. However, polarity related structure. Got it. So like dissolve like. Okay. Now look at the common one. Extend this question. Okay. And we know that, see, complete mix make a solution. So what's this? Water with methanol? Of course, we will discuss this one. Water with ethanol. When you see this one, can anyone tell me what you in your mind? What in your mind? Anyone? Victor? Can you help me? Thank you. Exact. Victor, exact. It's also chop. Also chop. Very good, Victor. That's why you always in the top. Number 1, top. Right? You see? So in this case, is what? The delta H is negative. The delta T is positive. Will form non-ideal solution. Will form non-ideal solution. Okay? We'll discuss it. Okay? Now, so those one also will form the water with acetone, or benzene with toluene. What's this? That is classical example from ideal solution. Ideal solution. This one also is ideal solution. This is the perfect ideal solution. Now, we are going to learn ideal solution. What's the mean ideal solution? Basically, you mix it, we can treat it as a diluting. Diluting. When solute solvent put together, that will have a diluting, which means delta H equals 0, delta V equals 0. We can add. If not ideal, we cannot add the volume, and the delta T equals 0. We'll discuss. We have one topic. Now look at it here. That's a common one. Not, of course, polar, non-polar, polar, non-polar. So DCM, everyone should know that, right? DCM, that's the density of organic solvent. If chlorinated, that density always is more than 1, always in the layer, upper layer, down layer, up, down, lower layer. Let's look at lower layer. Remember, chlorinated organic solvent, such as CH2, CHCl3, CCl4. That's very common solvent. Of course, it's very bad. It's a very bad solvent. When I was in Colorado cannot use this solvent. Cannot use it. Why? Because it's mile high. The vapor pressure, the pressure is low, so it's increase the evaporation. That's this the ozone, right? Ozone layer. So they cannot use it. However, that density always pass greater than 1. So that mixed with water, always should be lower layer. That's common sense. Matthew makes you to have one. Oh, which one in the bottom? You choose what? You choose chlorinated solvent. Yeah, either oxygen, that in the top, okay? So next one, see, that will not, this of course, why is it who use mercury? So we done this one. Very nice question. Very nice question, okay? Yeah, listen. This year this question. Next year you can change the same question, this solubility, not to change different combination. Is it possible? Of course. Now the question is why this one will not mixed? Why this one is organic layer? This is not you said, oh, this is a polar. It's not that polar. Matthew. Yeah, now go to next one. This one is a hard one. This is not a hard one. This one is interesting, okay? I will say. Argue this point. Daniel, until this point, it's hard or easy. It's easy, right? Well, it's very basic chemistry. Very basic. Very basic. Let me tell you, very basic. But they have lots of descriptive chemistry, have a lab scale. So we need to work on it. Now look at it. How are I going to make this solution sulfonic acid? See, to make this solution, of course, concentrated commercial available is 98%. D is 1.84 gram per ml. And that should be 18 molality. I remember this one when I was in middle school, because we use all the time. HCl is the same ammonia, nitric acid. You do know that, okay? So how do you do that? When we dilute, solute, more concentrated to less concentrated, always add solute to water. Slowly, at the time, delta H will negative, will release lots of heat. And now you have to let it cool down to the room temperature. Then, where you do this? the standard way to do that in the ordinary flask or in the beaker. Then you transfer to volumetric flask. That's the right way to do that. You cannot, you put water to volumetric flask, then you add acid to the volumetric flask. No, that's totally wrong. That's totally wrong. Volumetric flask, that one is have a marked 500 ml a liter. As you know that when change the temperature, the volume will expand or contract. You have to keep in the room temperature. Got it. That's when we make that flask in the manufacturing. You set up this. You got it. So now based on this one, then we could look at. And the choice should be this one. The choice should be B, okay? That's the one. Have to be, right? So you 0.5 concentration, this one should add slowly to not to make what? You make it 0.5. You are not going to make it 500 ml. No. Smaller amount water in the 1 liter flask, ordinary flask, or use a beaker. It's okay. Now, then cool down. That's to miss one sentence. Because in this case, we release lots of heat, lots of heat. The heat, sometimes even the water will boil. Yeah, water will boil. Now you let it cool down, then you add enough water. Now this cool down, then you transfer solution to the volumetric flask. Then use what? Use deionized water, wash the ordinary flask, then transfer to volumetric flask. How many times wash? Normally 3 times. Then use what? Use a pipette. You add water slowly or reach the mark. That's the way to do that. Okay, that's the way. Since from this year exam questions, we need to pay attention. Okay, and the rest doesn't make sense. Doesn't make sense. Now, can you give me 2 minutes? Let me tell you a story. Let me tell you the story, okay? That also will help us understand it well. When I was in the college, and that is 1980, my sophomore year. And there's a fellow from college. It's also is I think it's a professor or associate professor. To come to the college I'm attending, which is #1, specialized education. Right, that is a professor coming here, and everyone know that. Everyone know that when you dilute the acid, always add acid to the water gradually, right? But no one do the experiment. What he did? Now he was in our class, and they said, "Can we do some experiment?" And everyone get very excited. See, and they said, "Okay, we are going to test this theory." He put a container. This is a huge container. And this is 5 liter, okay? And in that container, he put probably 2 liter sulfonic acid. Okay? 2 liter. Now we are at least 30 meters away. We cannot surround it here. This is a problem. Now he used what? He used garden hose. Far away. Now you add the water. At the beginning, very slow. Water get in. Within a couple minutes. What happened? Matthew, can you imagine what will happen? And no, not the melt. And we see a lot of smoking come out. Then it's splash out. Yeah. So, how many years since that time to here? Almost over 40 years, I still remember it. That's the first time visually I see what's the meaning. So when you add water to sulfonic acid, 98%, generate a lot of heat. And let the heat boil the water, boil sulfonic acid, and they come out. How dangerous, very dangerous, if you do in the lab. So that's why, class, I really want you to pay attention to this one. When you do in the lab, do not use this. Also, do not use this one. How many? 0.5 more. That's not very much. Okay. Use a smaller amount. That's why. Okay. Now here, see. Right. You always heat. Why do this way? You want the heat to release slowly. Large volume flask. It's good for the mixing. Why use ordinary flask? Use a titration. That's very good for the mixing. Okay, that's the one. Now also it's good for the heat. After cooling, this here did not say it. The solution transfer then dilute dissolved volume. In the real lab work, we ideally transfer cool down solution to the volumetric flask. Then you go for the final dilution. That's the right way. That's the right way, okay? I'm going to repeat. The right way is what? You add acid to the water, then cool down. Then cool down. Where is, I said cool down. See? You cool down. Then you transfer to volumetric flask, okay? So that here, this question, the best way to prepare the solution. This one is related lab technique, safety, not the stoichiometry, okay? For concentrated sulfonic acid, always slowly add to the water, cool down, then dilute. That's the way to do that. Add, slowly, cool down, then dilute. That's the way to do that, okay? And now, you will take an exam. Of course, when you take an exam, you do not have a chance to make the solution. You do not have to, okay? Right? Okay, so we've done this one. Now go to next one. What's this? Oh, this is a good one. This question also is related lab part. It's related lab part. You see, if you know the lab part, this should be so easy. But most of the time, my feedback is that this question is so hard. Positive deviation, negative deviation in here is too high, too low. No worry. You understand the chemistry? So before do that, and in the class we discuss diagonal relationship. Did you remember? Diagonal relationship. Here is a magnesium, and that diagonal relationship is lithium. Okay, that's a diagonal relationship. As we know that lithium can burn in the air, you only get oxide, and also lithium can react with nitrogen gas. You get nitrite, okay? Right? Magnesium is the same. Magnesium is the same, okay? And the 3, 2, that's one. Of course, this is a white solid. It's a white solid. Of course, magnesium. And besides a question like this, also can ask you. You form two, right? You form two different compounds. Of course, will affect the stoichiometry ratio. Now, if we dissolve the water, what happened? This one, you will see ammonia. Double replacement, right? And that's one, this way no reaction because it's a solid rock. Right? Now, let's look at the question. So you look at this one, okay? So look at the question said, a chemist, let's say George, you determine fraction of magnesium burn, you make this one also because you will from this one too. Then you're going to find what's the fraction, right? You got it? So that's how can you do that? You know the mass this one. You add it to the water, mass, you mixture with this one. Can anyone tell me why? Why you need to add HCl? Can anyone tell me, class? We discussed if you were in the organic chemistry, right? Magnesium, it's a very reactive metal. And in the air, you form magnesium oxide, right? You got it? So when you add HCl, the purpose remove the coating oxide. The purpose you get magnesium, pure magnesium metal with power. And this reaction, did you remember the story I tell you? When I was in graduate school, make a very simple compound. Green agent, right? How am I going to make a green agent? You go to the literature, 100,000 literature. You said what? You use magnesium, you mix with under the THF, you do reflection, then you will get green agent. Right? I tell you this story in the organic chemistry class, right? And you know what? Make this reaction, spend my almost whole summer. Oh, of course, there's another reason, because in Beijing it's very humid during the summer. So this reaction, you should make sure it's 100% anhydride. But that time, no air conditioning, right? And the humidity very high. And also, even you make this one, it's destroyed. But the problem is not destroy this one. The problem is what? I did not wash with HCl. This is what? I'm going to reflection with this one. Of course, you will not get it. You got it. Yeah. So lab is interesting. You can, most of the time, you cannot read in the book. You have to do that. That's why the more lab we do, the better you get a feeling. Okay, it's not like we read a book. Read a book, you're going to get a high score in the lab. Very not likely, very unlikely. Okay, now go back here. So the reason say, so use this one to wash. So use this one wash, okay? Now look at the reaction. Now I'm going to go to the reaction. So for this one, the experiment is what? When magnesium nitrate, 3,2 is a solid. When you add to the water, so we have a double replacement. Did you remember when react with water, you always write H-OH. H-OH. So that here is a partially positive, here is a partially negative. Let me slow down handwriting, okay. H-OH. Here is a partially positive, here is a partially negative. So you get what? You get a magnesium hydroxide and ammonia. So here you the gas. Now look at, here should it be 6, and here should it be 3, here should it be 2. So that's the first step. Now next one is what? Ammonia is distillate. Ammonia, see here it's ammonia. You distillate, okay? To what? To HCl. And that one, it is excess. Exact. every time when I say excess exact, what's it mean? We will have a back titration. Back titration. Why? Because this one is the excess. It's exact. We are going to this is a limiting agent, right? So then we use what? We use base to do the back titration. Very nice. Also, you reagent lab. So you get what? You get the ammonium chloride. Now, because HCl, it is excess, it is exact. Then we got what? We use back titration. Back titration what? And it is HCl. Right? Now I'm going to analyze. I'm going to analyze this one, okay? Ammonia is distillated into excess HCl. The conclusion here, more magnesium nitride. Can I say have a more ammonia? Can I say will consume more HCl? Can I say this one? Right? Makes sense, right? Logical thinking, right? Okay, now, so excess HCl titration with the base. Now, what's the relationship? N 3 and 2, it's a proportional to what? To the N HCl added. Good with me? And that one is minus N HCl remaining. Clear enough? Now, the conclusion is that the arrow that make George think less HCl remain will make the calculation that one too high. Clear enough? I'm going to repeat. So the relationship is what? See, amount of magnesium nitride is proportional to the difference. The arrow that make the chemist think less this one remain will make a calculation this one too high. You got it? So based on this analyze, there is the only way it's a D. Rest one is too low. A, B, C, or A is too low. Calculate too low. B is too low. Right? C is too low. The answer is only D. Now let's look here. Why have this one? So look at, here's a summary. Here's a summary for you, okay? This one basically is what? It's a strategy. How can you look at this question? Back titration, right? Analyze, then ask, which arrow increase amount? Does increase find the amount? And what's the direction move to? That's this question about. The only choice should be D when the HCl solution was drawn into the volumetric pipette used to display the large bubble present. That's the D. Okay, go to the next one. Go to next one. Next one. This is also it's a common question, right? Do you see? One thing I can tell you, the choice should be this one. Should be D. Water from what? Water from network. The hydrogen is network. HCl, the hydrogen bond basically is what? That one is a linear, it's a chain. Basically, chain. The reason, look at water. You have 2 donor, 2 acceptor. Right? You have 2 donor, you have 2 acceptor. And HF. Although you have a 3 pair donor, but you only 1 acceptor. Water from network. This is for the chain. So it's a choice, and that choice should be D. I think it's a D, right? Yeah, answer should be D. This is an easy one. This is a very easy one. Okay, now let's look at what we can see from this question. Every time when you see the physical property, boiling point, melting point, solubility, vapor pressure, surface tension, capillary action, physical property, you have to look at the intermolecular force. When you look at the intermolecular force, you do not misunderstand. It's a total force, not the strength. You say, oh, HF forms stronger intermolecular force. True. But you look at total force, not a single letter bond strength. Very important, okay? What have a high one? Because they have an extensive 3D network. Did you remember? When we discuss intermolecular force, I gave you one example. It's ice. Look at the ice structure. Did you remember? It's a 3D structure. HF were not. See, look at the molecule. HF is a chain. Water is a 3D network. Ammonia is a very weak network. Okay, so take away from here, it's a common misperception is that HF is a stronger hydrogen bond, should have a stronger boiling point. No, it's not right. The water forming more hydrogen bond, create more extensive intermolecular network. So we look at the total force, not strength. Each question, so do have a meaning class. Meaning, now go to next one. This is a very hard question. I feel sorry. I did not, when we discussed thermodynamics, I did not send that paper to you. This question from a paper, identical. It's the same this one. But that paper is how many years ago? At least 10 years ago, this paper. This is an AP chemistry lab paper. It's a menu. Yeah, on my desk. I did not send it to you. If I send it to you, everyone will get it right. The answer should be 4.9 degree. 4.98 degree, okay. That's the answer. Now, how can I do that? How I can do it? Here, it's give you very detail. And this is a very hard question. Why? The hard question is really, how can you read when you do thermodynamic measurement? delta H, or equilibrium. How can you measure it? And that's the curve. So this curve is what? That curve is to measure the freezing point. Is right? Yeah, that's the freezing point. This lab is from physical chemistry. Physical chemistry, freezing point. Freezing point, we just learned it, right? So how can you learn freezing point? Delta H F equal I KF M. That's the freezing point. KF is constant. This one is molality. That one depends on van der Waals constant. If non-polar, you get a 1. It's it's non-electrolyte. It's 1 sugar. Like this one, this organic compound. If ionic compound, that should be 2, 3. That's why. Okay. Now look at the curve. The curve is very interesting. So you cool down. Basically, in this part is what? It's over. It is over cool down, right? Over cold. Now here you become crystal. You become crystal. So you become crystal. Now in crystal, you release heat. Now that curve, temperature increase. Now temperature increase until this point. Can anyone tell me why temperature will decrease? Can anyone tell me? Why temperature will decrease? Class? The temperature decrease is that the concentration is an increase. Because the freezing is what? The freezing is not, that's a solute. Right? The freezing is a benzene. Right? When this one freezing, which means you have less solvent. And now IM, it's an increase. So that one will decrease. Got it. Also, this is a very nice question. Now that one ask you curve. Which one is the right curve? So, because see the solvent become the solid. Now the concentration, no solute, no change. The concentration is increase so that the freezing point decrease. The freezing point decrease. Listen, remember, I'm going to repeat. For a solution, the freezing region slope slightly downward because as the benzene freezes, the remaining liquid, remaining solution become more concentrated. So that, and this one is a downward, see? Look at the slope. That slope is negative. Slope is negative, come from here. Very nice question, class. Very nice question. Now, how can you do that? We cannot just read this one. The way you need to use ruler. I don't know how to draw it. Use ruler, okay? Use ruler to do that, okay? Yeah. Visual idea is what? We look at, that's not draw, it's not right. See, the super cooling drop, then rising. And the still start of freezing at what? At this 4.9, 4.98. Take away is what? For solution cooling curve, reporting freezing point is not at beginning this one. No, it's not. That's not one. It's not this one too. It's not this one too. We needed to extend. That's the way to read it. Okay, very nice. Very hard question. If you get 4.98, give yourself 1 point. Now here I have something to say, okay? Something to say. What's the learning point? Every time when you see supercooling drop, then you will rising and slope freezing region. The freezing point should be determined by, here is the key. Extrapolation to the offset of crystalline, not taking the minimum temperature in this one. No, do not miss it. You not take this one, okay? Now, for solution, accept the freezing point of arbitrarily. So, yeah, you need to extrapolation. Simply read this one. That's not the case, okay? Why? Why need this one? During the freezing, temperature remain constant. We have this one. However, in this case, in the benzene, and it will have a downward. Why? We just discussed. Very hard question. I will put this question 5 star. Class, I want you to put a 5 star. Okay? Yeah, put a 5 star. Those questions, they can change, not give you the freezing point, but give you different curve and ask you which one is the right one. Why? Why? Remember this one, okay? Remember this one, okay? Now, just like the same, look at the ocean, winter, right? The ocean water freezing, and it's water freezing, the salt in the solution. And that when fresh water becomes ice, salt concentration increase, the freezing point will decrease. Exactly, it's this case. Okay, go to next one. This is the easy one. This one is the easy one. The vapor pressure of this one, what's this? STP, right? That's STP1 more liquid, butane, 0 degree, includes this one. Those questions many times. Every year has one question, different wording, right? And which one is right? Reach the equilibrium. Now, the answer is this one. If you get only one, give yourself a point. Now, how can you do this question? The step one, many ways to do that. If I were you, that's what I did, okay? What I did, I'm assuming butane, the 4H10. Not the equilibrium, or become this vapor, or become the vapor. So then I can calculate PV equal nRT. What's the P? What's the P? What's the pressure? Okay. And it's the pressure. If you do that, okay, you get a 0.996 atm. So basically, it's just like 1. Okay? Just like 1 atm. So tell us it's 0 degree. The 0 degree is 1 atm. Okay. 0 degree 1 atm. That's one. Okay. Now next one. That's the first step. The second step, consider is the insulation. The container is where, did you say here? I think it's some say here. See. So the vapor pressure, the evaporation require what? See, delta H vap should be positive. Should be positive. Got it? Because you see, look at vacuum, well insulated. This word is very important. Since no heat enter from surrounding to the system. Remember, no heat from surrounding to the system. And that one energy must come from where? Come from where? Come from this one. So the system cool down and the temperature will less 0 degree. So the temperature will lower this. I think that's right. Statement 1 is right. Okay, that is right. Now Y2 is not right. What happened? What happened when temperature cool down? What will happen? Let's look at. When as the temperature decreases, the P vapor, do you think it will decrease too? Right? See, the temperature decreases, and this one should be decreased too. At 0 degree, below the 0 degree, and can I say P WAP is less 1 atm? We calculate almost 1 atm, right? And we know log P equal minus delta H R 1 over T plus C. If we assume, suppose the 0.100 mole, or it's a gas, the P equal nRT divided V would be slightly less than 1 atm. When T that's 273 K. Right? So in this case, the gas cannot remain in the vapor. No. Gas cannot remain in the vapor. Why? Based on the definition. And the P gas equal what? Equal P vapor pressure equal what? Equal T. So not conclusion is that not all butane is in the gas phase. They have some liquid because temperature is less 0 degree or 273. That's why this one is a gas. No, that's not right. So that's the one. Okay. This question, as you know, that every year there's one question. Every year different wording. So that's I said it's a beautiful Olympiad thermodynamic phase diagram question. Okay. Every year, you look at it, in the last 10 years, every year have one. If I were you, I will look at the last 10 years, find all these questions, then you're going to compare, find the direction. See, at 0 degree, this one equal 1 atm, which means vapor pressure. Right? Now, any tiny amount evaporate, it could occur. The cooling lower the vapor pressure. Therefore, it's a low temperature, low pressure, some liquid remain. That's the one. Okay, can we continue? So how many questions? Oh, we are going to finish 30. Can we continue, Matthew? Or you guys have to leave? Continue? Yeah, let's continue. Okay, let's continue. Now, if you have to leave, you can leave. Okay. Yeah, you can get a recording. Let's do that. This is the easy question. This one is the easy question. Okay. Do you think I should have 16? Do you think it's a phase diagram here? I think it should have a phase diagram, right? Now let's look at cheaper point, this KR. It's a 0.73 bar. That's the cheaper point. triple point. Let me write more detail. Okay, it's a P triple point, 0.73 bar, and the triple point, the temperature, it's 116 K. At the triple point, what happened? At the triple point, this one basically is what? This question is related phase diagram and the triple point. At the triple point, the P equal this one. This one, the temperature this one. Now the condition is what? The condition, that's a triple point. Oh, here's the condition. The temperature is lower. So 90 K is lower 116. So that is below the triple point. Would you with me? So that point is below the triple point. That point is below the triple point, and also it's low temperature side. So it's only this one. Only solid. Okay. Only solid. Right? Below the triple point, low temperature side, only solid will exist. That's exactly I put it here. Okay. From thermodynamic, from phase diagram point, so below the triple point, liquid cannot exist. Agree with me? Only possible is what? It's liquid, it's solid gas. And gas is what? Around sublimation curve. However, here exact the pressure is 0.73 bar. You lower the temperature, lower the triple point. You move to what? You move to the solid area. You move the solid area. See, actual the pressure is lower sublimation, so that only this one solid can exist. Now, here is the strategy. The strategy is triple point question. Number one, when the temperature lower triple point, liquid not possible. Multiple choice. Liquid not possible. Okay. That's the law one. Law two, you compare actual pressure with sublimation pressure. If this one great, higher pressure, that is a solid. If equal, it's a solid and vapor or gas. If less, it's a gas. Very nice question. Often used in the USNCO National Exam, this type of question. So now 2-1 to law 1, law 2. Go to next one. Which statement about relative boiling point is correct? The answer tell you, you can grade yourself. Not this one, not this one. Both is wrong. Neither one nor two. Let's discuss. Okay. What the boiling point? What's this? 2-methyl. 2-methyl has a higher boiling point than. Doesn't make sense. Doesn't make sense. Why? This is a branch. This is isomers, same molar mass, non-polar, only have a random force. Random force depends on the molar mass. Molar mass is the same. Then determine the surface area. That's not make sense. Okay. Now go to next one. 1, 2, 3. With this one, higher normal boiling point than this one. That also doesn't make sense. Doesn't make sense, okay? But remember, so the key for this one is so easy. The branch always lower boiling point Why? Branch make a molecule more compact, decrease the surface area, lower the random force. Now, before I move on, I want to say something, class. When we compare the intramolecular force, we need it. What's the thing you look at? It's a similar molar mass. You have to keep the similar molar mass, like a candle, wax, solid, water, liquid. Right? Water, you have a hydrogen bond. It's network hydrogen bond. Polar, double force, random force. Why? Wax, non-polar, only random force. It's a solid. Why? Because molar mass. Okay. So this question we do not need to do that. This is so easy. Now let's do that. Okay, quicker do that. Okay. Now let me give you the answer. And that answer, what's the radius? R 144.1 pm. Give yourself 1 point. Right? How am I going to do that? So here's the phase center CCP, right? That's a CCP, right? Now, if I'm going to draw it, I draw this way too. Right? So you know what's this? That equals 4R. What's this? That's the A. The density 19.32 equal what? You have a 4. Let me write this down here, okay? Right. D 19.31. You have a 4. Why is a 4? 8 corner 1/8. 6 phase 1/2. That's the 4. So you get a 4. Then you find the molar mass. What's the golden molar mass? Let's look at golden molar mass. Gold. Where is the gold? Let's look at. It's a gold 197.197. 197. Okay, right? It's a 197. Okay, so you divide the Na. You divide the A the cube. Now find the relationship A square equals 16R squared. So that A equals 2 squared. Then you calculate. So this one, let's do that. 4 times 197, 6.22 times 23 times 2R cubed. Oh, cos R, you get what? You get a centimeter. You get a centimeter. Got it? So you get what? And that one, hold on. Let me make sure I get it right. Yeah, you get a centimeter, okay? Right. So you get what? You get, let me write it here. You get 1.44 times 10 minus 8 centimeter. So you get what? You get 144 PM. Right. 144 PM. Okay. So that's the way. That's the way. Okay. Now you get this one. So you get 144.1. That's fine. Now because it's here, use the 4 skin in the figure. Okay. Give oneself. Now go to next one. Oh, I see. I did it here. I did it here for you. Okay. Now this is a good one. This one is a good one. The answer should be 2. Give yourself a point. This is a good one. This is related to thermodynamics. So you have Rg. The Rg reacted to form Pg1 and 2. That should be isomers. And here is a diagram. What's this? This one is a delta G. Delta G, remember, why is it significant delta G? Delta G also has a standard free energy. Delta G, it is a state function, number one. Number two, it is an extensive property. And it's a state function. You know what it means, right? Now let's do that. Let's do the calculation. So the first one, I wanted to determine overall delta G standard. And we know R, G, PG, so delta G standard minus 150. That unit is joule mole. So I just save time, okay? Now, PG to P1, that equal plus 50. PG 2, you get minus 50. So in this case, you add, you switch, you add, okay? Right? You get RG to P1G. So you get what? And the delta G equal 100 joule mole. Now, RG to P2G, delta G, you get 200 joule. Can you see? Now let's look at now from here, what are we going to do? Look at this one. The mass RG equals 0. Since delta G equal minus 150 joule mole. So look at it. K equal what? Equal E delta G RT. You do the math, you get 1.06. So little bit greater than 1. So that R and the P is equilibrium. RT and the G equilibrium, so that this one is wrong. This one is wrong. Did you see? Right? That one is wrong, right? Now I'm going to look at the second one. For the second one, we are going to compare P1, P2. Now, for the P1, P2, and that delta G equal minus 100 joule K more. Right? How do you get 100? Basically, it's minus 50 minus 50 plus 50. You get 100. Give me a second, okay? Now K equal what? Equal P2, P1 equal what? Equal E 100 RT. So you get what? You get 1.04. 1.04. Can I say P2 greater than P1? greater than Q1. Do you see? Be this one. Now here is a key. Since P1, P2 is isomer, have the same molar mass, same molar mass. Look at this one. So can I say the mass of P1 should be less mass of P2? That's the conclusion. Really nice question. Hard question too. This is a hard question. So which means this one, it is right. This one is right. Got it. Okay, now let's look at what's the learning point here. The learning point is that delta G negative not mean it's complete. So we use this one to calculate the rate constant. And we can compare the delta G such as this one. Delta G, see, compare the magnitude delta G with what? With RT at room temperature. If delta G value only 50 to 150 plus minus, which means the equilibrium constant close to the 1. I want you to remember this one. So which means all the species under the equilibrium. That will help a lot when we do the question. Will help a lot, okay? Right. Now let's go to 20. This question is easy. This question is related thermodynamic and stoichiometry. So look at the reaction. So that's the acid with the base, right? You calculate this one. How are you going to do that? Since more, so we need to determine limiting agent. Now let's look at acid, which is 3.60 times minus 2 mole. Base, amine. So you get a 3.2 times minus 2 mole. Which one is limiting agent? Since reaction is 1-to-1 ratio. It is a 1-to-1 ratio. The limiting agent is this one. I'm going to highlight this one. That's the limiting agent. Okay, that's the first thing we decide. That is a limiting agent. Okay, limiting agent is what? It's this one, which means we'll take an exam. Okay, that's what we do here. Now, second one, we are going to calculate delta T. Delta T 22.0, 27.9. Can I say it's a 5.9 degree? I'm going to calculate the mass of solution. Why we do that? You give me a minute. That is solution. Where is the solution? So here is a 60 ml. Here is a 60 ml. Now we treat the density is 1, so that mass equal 100 gram. And the reason I do this one, I'm going to calculate the Q solution. Equal what? Equal MC delta T. So I got 2.469 kJ. Which means the reaction will release Q reaction. R and X should be minus 2.469 kJ. Delta H, R and X equal Q, R and X Divide what? Divide more. More is what? It's this one. It is a 3.20 times minus 2. So you get what? You get a 772 kJ per mole. However, you are not miss this one. That's minus. Why it's minus? The temperature increase. This reaction is exothermic. That's the way to do that. That's the way to do that, okay? Now here I give you, see, this reaction basically is what? It is a basic thermodynamic with Stoichiometry Olympiad question. So the first part, you need to calculate the heat release. How many more react? Then use this way to do that. Now, they do have a chart. For this sequence, the trouble is what? Use total mole. No, we have to use limiting agent. You cannot use total mole. Okay? Right? You cannot do total mole. That's the one. The second one, as I said all the time, you need to pay attention. Your sign. You pay attention to the sign. Okay? Pay attention to the sign. Now, the last one, everyone, I believe you should know that. The value large in magnitude, then 57. Normally it's 57. Stronger as the base. Matthew. Stronger as the base, it is minus, normally it's 57 kJ per mole. But here it's much, much more. What's the reason? That's the reason here. I really wanted you remember the reason, because it's a traditional proton transfer, also solvation effect involves the weak acid, weak base. I want to stay here 1 minute. Did you remember in the local exam that is electrolysis of KOH? Input NH is less than you measure the NH. Do you remember that question? And which tell us it's a side reaction. Titanium react with oxygen, release more NH. And here it's the same. This question, not related, same, but look at it. Also, it's a very nice one. You will not read it from any book, I tell you. So normally, stronger acid, stronger base will release 57 kJ per mole. That's the heat. When you do the lab part, you remember, you calculate. However, here it's more. Why? The reason because the proton transfer solvation effect for the weak acid, weak base. It's beautiful. Okay, now go to next one. Let's finish this part, okay? Finish this part. Good thing, I move everything for this section. 21. Now, what is this one? Let me give you the answer, okay? That should be 210 joule more. Okay, if you get 210 or close to 210, give yourself 1 point, okay? Now, how are you going to do that? How are you going to do that? And it's a way to do this question because they give you this one, they give you this one, they give you this one. You know how to do it, right? And it's a way to do that is that you are going to calculate delta HRNX standard. You are going to calculate delta GRNX standard. Then you are going to find out delta S, delta SRNX. You are going to find out. Then use what? Then use that one also equal what? MP SP minus NR SR. So you know this one through the combination, this one, then you calculate this one. Wow, that's cool, right? Hard, no, no. The question is, it's not from A to B, it's from A to C. You need to find the B. Now let's do that. But the first one, you need to write, you determine oxygen, right? And we know this, you should know this reaction. See, what's this? Liquid. That's the beauty. You should know this reaction. Balance. If you do not know this reaction, there's no way you can get right. No way. 100%. There's no way. Right? So everyone know that G R N X equal MP delta GF P N R delta GF R. You put the number. I calculated for you, okay? And equal 274 kJ. Now, not more. Because here is more. Okay. Now it's the same way delta H R and X MP delta HF P minus NR delta HF R. Do I have it? I have it. It's minus 200 kJ. So that delta G delta H T delta S delta S delta G delta H. Oh, no. No. That's not right. Oh, why? Give me a second, okay. And the delta S equal delta H delta G T. Then you calculate, you get 134 joule more K. Now that equal what? That equal 2S water plus S, not the delta S, oxygen, minus 2S. See, we know this one. And we have what? We know this one, we know this one, then you calculate this. Hard? No. Okay. Now let's move on, okay. See, that's the way to do it. That's very simple. As you calculate this one, it's very simple, okay. Now, this is a harder question, little bit harder question. Okay. The harder question is that the choice is this one. Now, if you get A, give yourself a point. Give a point. I'm going to not read the question. So this question related to what? Reading. So to read the graph, the plot, always important. Look at it. How many questions related to this one? More on the way. Right? So what's the foundation for this? I can't give it to you, see? And that's the one. This is excellent Olympiad question because what? You have to make this. Then you are going to look at the shape of the temperature with the heat add. Do not misunderstanding large Kp, which means the temperature rise. It's opposite. It's not. Okay, it's not. Right. So see, the question used now. Let's do that. We can look at this one later. Okay, I'm going to do here. Okay, this is a good question. As I said, last year, the question related to thermodynamics, we're getting harder. Next year, we're 2. So we need to spend more time here. Right? The question related to this one is that's right, the foundation relationship. Delta Q. Remember why I use delta Q, not the dq. Can anyone tell me why I use delta Q? Why? Because, very good, the QW is a passive function. You cannot use D, not use DQ, and use that one as high school AP chemistry use. That's totally wrong. Equal what? Delta Q equal N CP delta T. Why? Delta T is a state function. So that I get the dt delta Q equal 1 NCP. Now, from the temperature T with heat, see the relationship T with heat Q, the slope in the exam all the time, slope equal what? Equal 1 over NCP. Used to be, to use this one. Delta G, delta H, T delta S. Use this equation. Now, this year, to use what? Use this equation. Right. Slope. So what's this mean? Heat capacity. That one is larger heat capacity. And that is a smaller slope. Smaller heat capacity, it is a larger slope. That's the key. That's the key point, okay? The key relationship is come from, or you can write it this way. So Q equal NCP delta T. It's the same thing. It's the same thing, okay? I'm going to emphasize one more time. The temperature with the heat applied slope equal delta T Q proportional to 1 over CP. Then you know this one, you read it here. You read it, right? You read the CP graphing from 290 to 294. And the CP increase, that one is an increase. So the same heat cause the smaller temperature rise. Daniel, I'm going to repeat, okay? From 290 to 94, the CP increase, see, CP increase, right? The positive slope. Positive slope, right? So what's it mean? Same heat causes smaller temperature rise. The T with the heat, that should be less slope. Less slope. Less slope. Okay, now go to next one. From 94 to 95, CP dramatically decrease. So after the transition, the same heat causes large temperature rise. So that slope becomes steeper. That's the only thing match. I like this question. This question is very hard. This question is very hard. However, when we use this way to discuss, and it's make a perfect sense, class, make a perfect sense. That's a thermodynamic is the area we need to work very hard. We need to work very hard, okay? Very easy to do that. Now, if I give this question to you, if I give this, everyone can do that. However, the combine with the plot, the graph, you are going to read it. You are critical think, analyze. Okay. So now see here. When you will read this one, when you read the physical chemistry book, that's always like this one. Math. See, look at the relationship. That's activity. Okay. Very often you the exam thermodynamic. This one do not need to calculate. Basically, you need to just understand it. Just understand this slope with this relationship. When CP rise, slope decrease. When CP fall, slope increase. Today, I think it's very good one, right? Very good one. Now go to next one. Go to next. This is the easy one. Now, should it be C? Give yourself 1 point, okay? It's a C. Now, what is it? Grade is the molar entropy. Now, the key point here is what? Listen. The focus, the factors affecting molar entropy for the gas, of course. Right? Now, the complexity. You have a more atom, you have more rotation vibration, right? And also the micro states. That's the way to determine the entropy. That's the way to determine entropy. Remember, it's a great molar mass. Greater molar mass is great molecular complexity, more accessible energy state. That which you call this one. Normally, we did not in the thermodynamic. We did not spend time called microstate. That's related more accessible energy state. Right. For a question like this, you are going to look at the polyatomic. That should be higher than than molar. Then also within a class, the same class, you look at what? Here is not, see, you have 2 here, that's a 1. Now you look at normally large one has a heavy one, have a large one. Now I do find the data sheet. So hydrogen, it is 131. The unit is JK-mole. Hydrogen, helium should be lower, 127. Xenon will be higher, 170, because it's huge, right? And the chlorine, it is a 223. Those questions, if you will understand well, should it be fine? Okay, go to 24. Go to 24. The answer should be this one. This one. In a diabatic process, what means diabatic? We learn isoelectronic, right? And this one basically is no heat transfer to the surrounding system, which reverse that one well, right? And this is the easy one. Why is the easy one, class? ds delta Q reverse equal T. We emphasize 1,000 times. Because this one equals 0. Of course, this one will equal 0. Right? 2 is right. Now, do you think that one will equal 0? Why not? Why? Not necessary. And we know that H equal U plus PV. That's a definition. Of course, some book use E. Only American use E. In the world, around the world, all use U. Okay. Right. And delta H equal what? Equal NCP delta T. Since the delta T generally change, that not equal 0. So that one should not equal 0, okay? Should not equal 0. Now, here, I summary for you. Summary for you, okay? At diabatic, Q equals 0. Isothermal, T equals delta T equals 0. Isothermic, delta H equals 0. Isentropic, delta S equals 0. Reverse diabatic, it is this one, not this one. Because I want you make notes. It's not delta H, okay? It's not delta H. That's why the first one is wrong. Understand the distinguish is very valuable for the exam. Not only USN or even IHO. Now let's move on. Oh, last question. Last couple question is chemical kinetic. This year, there's one question I like it. I really like it. One question I really like it. We will show you. Okay. So this question is easy. Did you remember in our class, chemical kinetic, we spend lots of time. We have one special class called Beyond Ordinary Reaction Order. Right? So they said irreversible reaction A take place, it's the rate. K, that's the rate law. The rate of equal KAN. And the half-life independent A, what's the N? Do you think it's so easy, class? Do you think it's this one? Right? No. Here I give you this one. Did you see? Zero order. 1, 2. That's the integrated rate law. That's it. That's it. So this question send you points. This question send you points. Okay. So answer is now go to next one. 26. This is a good question. I like this question. Okay. I like this question very much. Why? Let's look at it. As the catalyzed reaction first order, okay, it's the first order. That's the rate. When pH equal what? Buffer 5.0. What's the rate when pH buffer to the 5? Because it is the first order, and the rest react is the same, okay? So first order, can I say K equal H plus? Can I? Can I? Right? Okay. So what I'm going to do is when pH equal 5.0, now we can calculate concentration, okay? When pH is 5.5 and it's a 10 minus 5.5 m. Now, if I'm going to ratio 2, 1, do the math, and that should be 10 minus 0.5. You should equal what? 0.316. Right? Very simple. Now, the rate 2, the rate 1 ratio, right? Equal what? Equal K H plus 2, K H plus 1, K canceled. And that equal 0.316. You know this one. You know this one. So I get rate 2. That should be 1.0 times minus 6. Put a unit. M second. M second. The unit is very important in the chemical kinetic, right? Got it. So if you get this one, give yourself a point. This question, see, do you see? That's the way to do that. That's the way, okay? That's the way to do that. It's very easy, my friend. Okay, this question is a very good question. This question is very good. Read the question. They said decomposition of hydrogen peroxide from water oxygen. We just so in this set, we all did one question. Okay, that's the second one. You know how important, right? Right, very important, very important. Now it's what? They use lots of catalyst. I minus could be catalyst. I minus catalyst. Now they said what? This is the key. This one I minus is a catalyst. Think about what's the catalyst. Consume, regenerate, consume, regenerate, which means that one is a constant. Class, if you know catalyst is lower activation energy, it's a consume and regenerate, which means centrally is a constant. Now, question is so easy now. The rate equal K I minus K prime. Basic question become, if I write the question for you, it's a pseudo first order. Everyone knows how to do that. Here they introduce the catalyst. Basically, it's a pseudo first order. So K prime equal what? Equal K I minus. Right? Now you know this one. Then everything is so easy, right? Everything is so easy. See, K minus equal what? Equal K is 1.05 times 0.300, 0.35 minute. It's a minute. It is a first order. It's a first order, so that it's a first pseudo order. Equal what? Initial E minus K prime T. Then you just put the number to calculate. You should get 621 times minus 2. If you get this answer, give yourself another point. Okay, another point. Okay, now look at here's the important one, class. That's the learning, Olympiad learning. Okay, big chop is what? Catalyst appear in the rate law. However, catalyst overall reaction will not. The question give you fake news, not a fake news. Look at 3. That's one. This one equals 3. What else? Oh, see, they give you both is a 0.3. I said, wow. See, but you know what? Why is a constant? See, this is not equal. E1 initial both is this one, but I minus is no change. If you know this one, this is good. See, the important for this question is what? See, catalyst. Now I use catalyst. Next year, Emma, they may use different catalyst. And if a catalyst is constant, you get what? Use OBS, observed rate constant. This is a constant. See, then you use the first law to do that. I like this question. I really enjoy this question. This is a very good question. Okay, now let's move to the next one. This one is easy. This one is easy. Okay, why is it easy? The basic use this equation. Basic use this equation. So you get a Arrhenius equation. K equal A E EART. Now you basically get what? You find it's EAR. You see EAR. Then you how are going to do that? See, you get EA. Then you compare. Okay. You do not need to use log. Okay. That's another way to we did it in the class this one. We did it in the class. So when you do the math, you compare this one. See, you compare K with that formula. K compare with which? With this formula. But it's ratio. It's a ratio form. So activation energy for this reaction, I give it to you. Okay. EA, let me find out. And equal 9.89 kJ per mole. If you get right, give yourself a point. Okay. This is a very, very common exam question. Okay, so give you K this form. Then you know the EA, right? You can use this equation. So you get what? You compare. You just compare, okay? Right. Now, one thing I wanted to add is that for advanced insight, the relatively small activation energy, that's 10. See, that's 10. That reaction is not sensitive to temperature. Did you remember? When activation energy big, very sensitive to the temperature, very high, this is moderate. You should know that, okay? You should know that. And last question, 29, 20, 30 is very easy. This is very easy. Let me give you the answer first. What's the rate law? Let me write out. Then we are going to do that. The rate law is the rate equal K first order, okay? Right. That's the one. And the second one, what's the one? That's this one, okay? So totally 30 questions. Now let me do one by one, okay? Let me do one by one. How to get that? So from here, see, here is the slowest step. In order to do that, we need to write rate constant, right? So if I said that here is a K1, here it's a K1 minus 1, here it's a K2, here it's a K3, here it's a K4, and here it's a K4 prime. So that this question related to what? I hope you still remember that's related to pre-equilibrium. It's related to pre-equilibrium, chemical kinetic. Pre-equilibrium, okay? The slowest step is this one. Now we write the rate law, okay? So rate equal what? Equal K2. K2, where is the slowest one? And it's this one. Okay, I got it. HCO. Okay, give me a second, okay. HCOH, OCH is a plus. The water is a solvent. Water is a solvent. As we know that, what's this? That is intermediate. That is intermediate. Now, see here. And that's called a pre-equilibrium. We're going to discuss what means pre-equilibrium. So you reach equilibrium first, establish the equilibrium. Now you are going to form the product or intermediate. That's called, so that we can, pre-equilibrium, we can treat it as equilibrium, okay? We can treat the equilibrium, which is K1. Let me got it, K1. CO2, HCO2, CH3. Right, equal what? Equal HCOH, OCH plus. See, equal, you. Now, here is a K minus 1, okay? So that your rate is what? Equal K1, K minus 1, K2, K minus 1 equals HCO2, CH3, and H plus. On that one, we get a K. See, HCO2, CH3, and H plus. So that's the one, okay? That's the one. Got it? Now, let's look at the next one. Let's look at the next one. Which one? Here is a reaction mechanism. Here is a coordination diagram. Right. From here, step 1. Step 1 is fast. Step 2, slow. What means slow? Which means larger activation barrier. Step 3 is fast, smaller barrier. Step 4 is fast favorite, smaller barrier. Product has lower NH. Now I'm going to repeat. The first one, unfavorable. What's mean unfavorable? Fast, which means smaller activation NH. Unfavorable, which means the product intermediate high NH. I'm going to repeat, Emma. Step 1 is a fast, unfavorable. What's mean? Which means activation NH is small. However, the product in here, of course, is not the product, it's intermediate. It's a higher NH. Unlike this one, the fast, lower activation NH, smaller one, but the NH favorable, which means the product have a lower NH. Based on this one, that's the only one. That's the only one fit this pattern, okay? So I think that's it. That's it. Now, do not go away. Ask your question, okay? I'm going to, next time, I'm going to finish the rest, the 30 question, okay?